The world is a little different now. It's shocking how fast it unfolded.
Also, people were basically starting to work more like you've been doing for a couple of years, which is basically smart working all the time, right?
Yeah, I've been working on my own over the internet since, I guess, 1999.
Wow.
Well, let me do it. Physics was a little ahead of the game because we share all our papers over the internet, and that happened very early on in the 90s.
Mm-hmm.
So that meant I didn't get locked to a library or to a university even, and I could pretty much go anywhere I wanted in the world with good internet connection and do my work from there. So that's when I split off to Hawaii. That's a little bit ahead of the pack.
That's right. And is there, in the way it works for physics, and I think in general with science, does all collaboration work? Well, let's say you deepen a subject, you do your work, you come up with a paper, and then people criticize it for a couple of years until someone else comes up with something better or works on maybe demonstrating your theory or things like that. And
what usually actually happens is people take a piece of your work and incorporate it into theirs.
Okay, so it's like building on top of yours, and then you move forward like that.
Right, and people learn things from what you've done, and then they do their own thing, and it grows that way in different directions, at least for theoretical research.
Do you see that as a positive thing or a negative?
I see it as a positive thing when you're searching a landscape of possibilities for some specific prize that you want to find, but you don't know exactly where it is or how to find it.
Mm-hmm, mm-hmm. So it's there, and someone else is looking with you.
Right, but you don't want everybody looking in the same place, which is sort of what theoretical physics has mostly been like for the last 30 years.
Okay, so that you're referring to string theory in that case.
That's right.
Yeah.
So most of the community has been working on string theory and using supersymmetry and these other theories, and it just hasn't really panned out. And now everybody's sort of at a loss. Well, what do we do now? And they're still trying to work on those ideas and offshoots of those ideas. But really what you want is a lot of smart people looking along very different avenues and
mm-hmm.
not just where the whole herd is looking at once.
In terms of process, wouldn't it be easier, and that's just a question for out of curiosity, if people literally sat down and brainstormed things together, or is that just not possible?
Well, we sort of formalize that in conferences. So a conference is sort of a big formal brainstorming session where people come forward and they schedule their talks and they give their talk about their ideas, and they get feedback from their crowd. And a lot of times that feedback results in collaborations where people will go off and work on a combined idea together or something new. And so this is really what conferences are and why they're so exciting, and also why I kind of miss them. But they're also often in pretty locations. But that is basically what a science conference is. It's a big brainstorming session.
And it's always been like that. Like I remember mentioning conferences from the Einstein and when he was presenting his theories, and then there was on the other side maybe Bohr with quantum mechanics together with Heisenberg.
That's right. It's very often where theories first see the light of day.
Gotcha.
It's where physicists share their ideas with their peers.
Must have been amazing to assist to one of those. And are they normally streamed, or is it like private conversations nowadays?
No, so most of them are actually now streaming. So you can just drop in on a on a physics conference without an invitation and attend it, but you can't give talks. The talks are scheduled.
Okay, of course. One question I had, and I think so the way I structure normally these conversations, again, they're very informal, and I really apologize for the level of ignorance that comes out of sometimes the questions. And some might be very basic, some others may be, I don't know, maybe beyond above the line in terms of approach. But really take it as a spontaneous conversation as we were meeting on the bar, and I was generally curious about the work you do and how it works. So the first thing I thought it would be useful to start from, and again, apologize for being very basic in the approach, is I found this quote from Galileo Galilei, of course Italian.
Of course.
Which is interesting because he mentions the relationship within the universe and its language and mathematics. So I think it's a very good tie to then explaining what theoretical physics is. And I'll read it out loud so you can tell me what you think of it. So the universe cannot be read until we have learned the language and becomes familiar with the characters in which it's written. It is written in the mathematical language, and the letters are triangles, circles, and other geometrical figures, without which it is humanly impossible to comprehend a single word. This is Galileo Galilei from the Essayer in 1623, so yes. 400 years ago, basically.
Yes, I'm familiar with it. I think he was spot on very early on. I mean, that's absolutely correct, and it was really. I mean, that's really why I first got into physics, is I found I had a facility for mathematics at a young age. And I also loved reading science fiction and fantasy novels where you have sort of these magical powers and there are mages who study these arcane languages that are then able to understand and manipulate the world better through this arcane magical language. And then to find out that actually this exists in our universe and the magical language is actually mathematics that is behind everything that we see, and to find that out was just really fantastic, and that's how I got hooked. So it's very much the case that mathematics is the language of our universe.
It reminds me that Disney movie, who's that, Donald Duck in the World of Mathematics, where he's basically bringing us back into the ancient Greece and how the Greeks approached mathematics and finding geometry behind everything.
Right.
So it actually goes
they
back.
They also very much thought that mathematics existed independently of the physical. That it was not a human creation. It wasn't even part of the physical universe. That mathematics had an independent existence for its own sake.
In this matter, do you feel it's more of something we've discovered or an invention, therefore?
Very much something that we discover.
Okay, so it's like it's exactly the way things are written, and we're discovering that language as we move forward.
Precisely. So if for aliens elsewhere in our galaxy who develop sufficient sophistication in mathematics, they will find many of the very same mathematical structures that we have found. They'll discover Lie groups, the classification of Lie groups, how symmetry works in the abstract, and the real numbers or something very much like the real numbers. I mean, all these things are just general things you can discover playing with mathematics, and that would be developed. It's universal, and it's beyond universal. It would exist independent of universes.
I find it so fascinating. I mean, there's so many fields, of course, beyond the theoretical physics where basically that applies. And of course, there's music and so many other places where you actually see mathematics in action. And it's just mind-blowing how much everything is so connected in a sense.
But I'd say the vast majority of things that we touch as humans are human creations. Yeah. So if you're composing music, you're still working with a human created musical scale, and you can work with different scales of notes. There are whole different systems of music. We have just settled on one. But so alien music is going to be very different than ours, and beyond just being in a different frequency range. But for mathematics, it's something. I mean, one of the reasons that it attracted to me is it's completely independent of humanity. I mean, it's pretty much the opposite of studying law or something that is completely, created by mankind.
Gotcha. Reminds me of that quote from Neil deGrasse, who said that science is under no obligation of making sense to us. So
that's right.
This probably is reinforced by what you just said, which is like it's there regardless of the fact that we're here reading it or not.
Yeah, and it's quite astounding that it has been so accessible to us at all, at least for the past couple hundred years. The last 30 or 40 years have actually been rather rough for fundamental physics, because we have not been discovering new particles or new physics anywhere near the same pace as we were in the previous 100 years.
Yeah, which with our computational power, you would expect things to grow very quickly in that direction, right?
Right, but things have all the low-hanging fruit has already been picked. So now to find new information about fundamental physics now takes a much stronger concerted effort. So that's why we have very large experimental collaborations and things like the Large Hadron Collider that require that are very expensive to build and require a lot of community effort.
Energy. Yeah, and energy. Can you help me break down the relationship between a theoretical physicist and the experimental physicist, now that you mentioned it?
Yes, well, pretty much this happens at university. You sort of get an idea whether or not you like tinkering with equipment more, or whether you like playing with the mathematics more. And if you're more mathematically inclined, you tend to go more towards theory. And if you're more like hands-on doing experiments and thinking up very clever experimental apparatus to invent and implement and find new things that way, you go experimental. So experimental physicists very early on tend to spend a lot of time in the lab working with equipment to find new stuff that way. And it also tends to be very practical, right? Because this also often translates to things you can do to advance technology, to make inventions that get used by industry and make people a lot of money. So experimental physics tends to be much more practical, whereas theoretical physics, it is connected to experiment. You do want to work on theories that are in principle testable, but often you're working with mathematical models that are very far removed from physical experiments, and you're just trying to work with mathematical structures and match them up with known structures that have been established experimentally.
So they sort of they sort of need each other, but not necessarily. They rely on each other, but not necessarily need each other in terms of. You could go on with
in order to be science, they do need each other.
Okay.
So there are theorists who sort of will go off and float off into the clouds and never make contact with anything that's in principle testable. And it's been called into question whether they're still doing science. At that point, they're basically just playing with mathematics that is not even in principle testable, because it's not science until you can test it and do experiments that will either validate your models or invalidate them. And this is very important, because there's an infinite landscape of mathematics to explore, but we only live in one universe with one set of physical rules.
Yeah. Otherwise, you're basically doing philosophy, sort of. Yeah,
that's right. So, and it can the way progress actually happens is it can go one of two ways, or a mixture of both. I mean, either some theorist can come up with a new model that predicts a new particle or a new phenomena that exists, and then experimenters see that and say, okay, well, I'd love to be the first to discover that, and they go and look for it and see if they can find it. And if that happens, then that's great, and the theorist was there first with the idea, and they get more the notoriety and prizes for that. But also it can go the other way, where an experimentalist is pushing things on the experimental side, and they find something that theorists just didn't predict. And then the theorists are then in the position of scrambling to come up with a model to describe the new experimental result.
Gotcha. So they need data anyway to work on the back of. Of course, the more data they have, the more precise they can be in the direction they're taking with their theory.
Yeah, that's right.
Sometimes I assume that you would also have a theory that's not demonstrated until you're dead, basically.
Sadly, that could be the case.
Which might be frustrating.
Yeah, so it's that's the case when you're working on any very hard problem. So if you're working on something that's very, very hard, it's very easy to get frustrated, and because it's very hard to make progress, of course. And often progress could be made after you're gone, and your work would only then be appreciated, which isn't very satisfying when you're alive.
Absolutely.
So basically what you want to do is you want to make sure you have a very good life independent of the hard problems you're working on. So if you're working on a hard problem in physics, or if you're working on some hard problem in computer science, or anything that is just very tricky to make really good progress, you want to make sure you have a very good system of support for the rest of your life. You have that you have a good financial safety net. internet and a good social network and friends and relationship and all these things supporting you. So then you can work on this harder thing that would be fantastic if it worked out. But if it didn't, you still had a good life.
Yeah, exactly. So there's a book I'm reading these days. It's about multipotentialities and multipotential. How do you call them?
Potentialities, yes.
Yes. And I was exactly thinking of what you just said in these days, because while I was reading it, it's laying down two different approach, and that's not just necessary to research and science, but also in any business or a work field that you would work. So you have the very vertical people that dedicate their entire life into one single task, and might succeed. Imagine that as being the sports person that's doing surfing all his life and just surfs and just takes waves for all his life, and that's his that's going to be his job, and that's going to be what he's going to live out of. And one day the injury can come over, and that's completely over, and his life is completely fucked. Or he becomes a very well-known international surfer, and he's famous, and he lives on the back of that for his entire life. There's little else in that case, because you're dedicated your entire life. So I don't know how many hundreds, thousands of hours
this
just in
the gamble
perfectioning
that Olympic athletes often make at a young age.
Exactly. On the other hand, there's people who are the ones that normally get asked the question, what do you want to do when you grow up, when you're an adult, and they're in crisis because they have no clue, because they don't have one specific passion, they just love everything.
I think those people have happier lives.
Yeah. I think the point that Brooke is going to make, I'm still at probably page 42. I've got a lot of 1/3 of the way done. But I think it's exactly where the place this book is going, which is, the richer you are, you become richer in terms of person if your experiences are richer. And sometimes there's a cross-pollination of information that you take from one place to the other. And that happens to me in my daily job. When you're dealing with having to find ideas and solutions to problems. And I think it's the exact same thing that happens to a scientist sometimes, maybe not all of the times, because we know a lot of histories of scientists who have dedicated their entire lives, and artists who have dedicated their entire lives to the craft and almost just died by doing it. But then on the other side, as you said, balancing out things maybe would give you a more sane. It's a safer and more maybe even rational approach.
It's more psychologically healthy just to cultivate balance in your life.
Balanced is the word.
Anytime you're completely obsessed with some goal or task or anything, if you fully dedicate yourself to it, and then it doesn't work out, you're going to be utterly crushed. Whereas if you spread your interest out and you try new things and you have new experiences, it's just much healthier and happier as a human being.
Absolutely, totally agree with you. And is this basically the reasoning that brought you into living the way you're living now?
I also really love surfing and playing in the ocean, and that's it makes me really happy, just in a very direct, physical way, to be that immersed and connected with nature. So I really love it and love spending my time doing that. So I try to balance my time between intellectual work and just playing outdoors, and also interacting with other humans.
It takes a lot of rigor anyway to keep you concentrated and find the space and the headspace to actually remind yourself that every day you got also this other thing to do, which I think comes with experience. Absolutely. You mentioned the passion for like everybody of us, science fiction and so on. I actually have an interesting question. I hope it's an interesting question. Can you imagine of any other way to describe a wormhole other than the way it's done in every single space movie, where there's basically this piece of paper, 2 points, there's the question asked, what's the closest way, what's the shortest route between these 2 points, and then they say, it's a straight line, and then he folds the paper and they basically digs a hole into it with the pen. Is there any other way it can be done?
Well, the idea is to do that with four-dimensional space-time. So with wormholes, you can construct wormhole solutions to Einstein's equation. So it is a possible thing that you can do with space-time, is have a wormhole. But in order to build it, you need this special sort of matter that anti-gravitates. So you need matter that pushes other matter away from it. And as far as we know, there's no such thing. So as far as we know, wormholes cannot exist because there is no anti-gravitating matter. There's no matter with a negative energy density.
Okay, because it would have to bend the space-time in a way that with the matter and energy we have today.
That's right. It would basically fall up. And so you can't, there's no such stuff as far as we know. Even antimatter falls down. So as far as we know, there's no upfalling matter. So you can't actually build a wormhole, because that's what you'd need to open up the throat of the wormhole to be able to get out of it. So all we can build is black holes, which are one-way wormholes to oblivion. So you just fall in, you can't fall out. So,
since you mentioned
that picture,
black holes,
that picture is a reasonably good one, where you're basically connecting two distant points of space-time by having a shorter path between them that doesn't go over the paper, but goes like between points on the paper through a trickier way.
Yeah, I think it's the best way to explain it. It just annoys me that it's always explained in the same way, and so you have this thread between old movies where there's this guy who's always asking the same question.
Right. You can be either more annoyed or less annoyed by the fact that they can't actually exist.
Yeah, that actually helps me, because then. So you mentioned black holes, but I think one way of getting to the theory of everything is probably, and that correct me if I'm wrong, maybe starting from Newton and where he started to basically connect the fact that there were some rules that were guiding the way objects would move here on Earth, that probably would be the same, more or less, of the rules that were governing how planets were moving around each other. Then getting into Einstein, and then getting into general relativity, and then the comparison with quantum mechanics, and then the theory of everything, which probably is trying to merge these two fields.
Yeah, it's the ultimate progression of that so far successful strategy. And you're absolutely right. I mean, it comes from, Newton saw that there was this universal law of gravitation. There weren't different rules that the planets were following from what things would follow here on Earth, that they're all following the same rules of gravitation that explained both, which was fantastic. And coming up with calculus also helped develop that and explain it further.
Yes.
So it's not just these ideas of unification. It's also the development and use and discovery of more mathematics that helps you progress things this way. Same with Einstein, and his using pseudo-Riemannian geometry for describing general relativity and gravity, which is an astounding jump for its time. So that was really, really pretty fantastic. And I think there are more jumps like that to be made, which is so we're actually living in a very wonderful time when we don't have the complete answer to what the ultimate mathematical structure of the universe is, and we as humans can still have a shot at looking for it.
I see this pattern of things being merged more and more, right? So space and time, and then now trying to merge general relativity with quantum mechanics.
And even electricity and magnetism were thought to be two very different forces until Maxwell came up with a combined description of them.
Exactly.
Yeah.
Exactly. How can I understand these? How can I understand and explain these four forces that we're trying to merge all
to
together?
understand the known force. So we have electromagnetism, and that people are familiar with is light and photons. You see, if your eyes are open, you're interacting with photons. There's also the weak force that has to do with the radiation from atomic nuclei, and the strong force, which binds quarks together inside nuclei, and the gravitational force, which we already talked about. And all of these forces are described using the geometry of Lie groups and fiber bundles.
Already, is that proven?
Very
or
well
is
known
that,
since the 50s. So there is a geometric description of the known four forces using basically high-dimensional symmetric shapes twisting over space-time.
Okay, so Lie groups are geometrical shapes that are symmetrical and a bit hard to conceive mentally because they're just on more dimensions than
right. You can conceive of like a sphere as a nice symmetrical two-dimensional shape, but these things get 3, 8, hundreds of dimensions, and they're with very complicated twisting structure. At which point you can it's easier to work with the description of their shape than try to think about the shape itself, which we can't.
Gotcha. Because E8, how many dimensions would it have? Boom. Okay. Yeah. No. Better to stick with the.
Well, but what they found even back in the 50s and 60s and then more in the 70s is that if you're using Lie groups to describe fundamental physics and these fundamental forces, that for each dimension in your Lie group, you have a different kind of elementary particle. So there, for example, for the strong force, there are 8 different kinds of strong force particles called gluons. And that's because SU3, which is the name of the Lie group that describes the strong force, is an 8-dimensional Lie group. And the way that Lie group geometrically twists around within itself describes the strong force charges of those gluons, and also how the quarks also interact with that Lie group.
Okay, so is that in the way we see those gluons, is that the expression of some sort of, how would you call it?
I'd say it's an excitement of that Lie group over space-time.
Exactly, but we're only seeing the gluon because that's the reflection on our three-dimensional universe.
And that's not really a reflection. It's more of how the Lie group is twisting over our space.
Okay. So it's like one dot in the multidimensional.
Yeah, and another way to think about it is if you think of our space-time as a 4-dimensional geometry that we're moving around in.
Yes.
Then these higher dimensional Lie groups are attached.
Sorry, why 4 and not 3? Because you're putting time in there.
3 space and 1 time.
Okay.
So we're living and moving in this 4-dimensional fabric, and if you imagine that it's not 4-dimensional, if you include the strong force, it's 12-dimensional because you have the 8 dimensions of the strong force. But these strong force dimensions are very symmetric, so we don't see them. We just see the 4 dimensions that we can move in. But the way this whole 12-dimensional fabric twists, if it twists in a certain way, it looks like our 4-dimensional space-time with gluons in it. All right, and that's because of the whole 12-dimensional thing is twisting.
So if I see a gluon moving in space, in my 4-dimensional space, that's the reflection of what you just described, which is the twisting of the 8-dimensional structure. Can I call it structure? Or whatever.
So my best idea for what the universe is it's this sort of high-dimensional twisting geometric fabric.
How the hell do you? Well, let's say I'm an experimental physicist and I have to demonstrate this.
Well,
how can I do it?
As I said, for each different dimension that a Lie group has, there's a different kind of elementary particle, and so they have a very distinct signature. So if you have a proposal for larger Lie groups, that you think might describe our universe, then that should predict new particles with those predicted properties that can be searched for.
Okay, so it's just a matter of finding them.
But of course, it's not that simple.
Or not finding them. Because not finding them
just means that your picture is a little off. And I don't currently have a good picture. E8 is not a complete picture. It's an amazing, you can call it a coincidence, that the structure of particles that we see, at least with electrons and up and down quarks and electron neutrinos and so forth, as well as all the known forces and gravity, that entire structure does embed in this E8 Lie group.
But can it really be a coincidence? Like it's ticking so many boxes.
Too cool to be a coincidence.
Exactly.
So I think there's something fundamental there, but E8 also doesn't describe the other two generations of matter. So it doesn't describe like muons and tau leptons, for example. It doesn't seem to describe this correctly.
Mm-hmm. Mm-hmm.
So there's still some problems. So there's some hints that it's on the right track, but it doesn't seem complete, and there's more searching and more work and more figuring out to be done.
So your paper, which look, I think I opened it up a couple of hours ago. It's the exceptionally simple theory of everything that came out in
2007 or 8.
7. Yeah. And then since then, now it's out there, and now people are trying to either prove it or disprove it.
Well,
like
some string theorists came forth and said they disproved it, but it was a little bit intent they did.
Of course they did. Okay, but anyway, that's the way it works. Like, so you propose the theory, you've got your maths, which, by the way, you're calling it exceptionally simple, which, of course, because it's very elegant and makes a lot of sense. Now that we explained it, but
it was
looking
also,
at the maths.
There's a little bit of irony and humor in that title as well, because, of course, any theory that's going to have a shot of describing elementary particle physics is not going to be especially simple. But it was
exactly. Well, not for the common human being like me. Like, it's I can't read it. It's just.
But the mathematical humor came from the fact that it employed the E8 Lie group, which is called one of the exceptional Lie groups. So that's where the exceptional came from, and it was called simple because it used only one Lie group to describe everything, and that when you use just one Lie group, that's called a simple Lie group. All right, so it was a mathematical pun as well as some irony. So I will live with that title.
To be honest, I wasn't expecting it to be so clear, and I'm really glad that it actually came out, even just without pictures, which normally are very, very well appreciated when someone's explaining something this complex.
I was actually,
maybe complicated.
I was working with matrices and equations and all this, and I was astounded and delighted to find out that a lot of the structure that I was working with actually could be described in these very pretty diagrams. And these diagrams are the projection of the charges of elementary particles that we know of along different axes corresponding to the different forces. So, and if you do these plots, you end up with very pretty patterns in up to 8 dimensions or so.
I'm gonna use this picture so that people know what we're talking about. Maybe as the cover for the episode.
It was astounding that these the math I was working on has this very pretty representation in terms of diagrams, in terms of weight diagrams.
What am I looking for? E8 Lie group. Okay. So I'm gonna Google it and take one of those. This is more of me trying to understand a bit better what we just discussed, which is now we've described the sort of projection of these forces from a higher dimensional space. It reminds me a lot of, well, not necessarily, but there's a bit of Interstellar, because there's the higher
Interstellar
dimensions.
Actually, that movie did a wonderful job of portraying a black hole.
Yeah.
Right. In terms of how the black hole would curve the light around it. So what it would look like. So you're actually looking at what's behind the black hole, even though you're in front of it.
Yeah, you're right. And then it was just a coincidence that a couple of years later we came out with that picture, which is exactly the way the black hole was represented in the...
Yeah, pretty amazing. It was absolutely, and it's just fantastic. We're actually able to image a black hole, which is something that I never thought would happen in my lifetime.
What do you think of, talking about Interstellar, because you have higher beings that are living in a world which is higher dimensional, and then you have him trying to communicate, Matthew McConaughey trying to communicate with the real world.
I thought that was entirely fanciful. but the portrayal of the black hole was good.
Okay. So that's a stretch.
The problem is you can't, once again, same thing with wormholes. You can't affect things backwards in time without matter that anti-gravitates. So in our universe, we can't have what are called closed time-like curves, which means there's no time travel backwards. You can time travel forwards in several different ways, which might be fun, but
just you could, okay. That's nothing you could do with the
it does.
Twins
so you can time travel the normal way, right? Just by sitting there and traveling forward in time the way we almost all are.
Okay, just waiting for the time to go by.
Or if you can slow yourself, if you can go faster, right? And you can slow your own clock down. And then when you come back, everybody else will have gone further than you in time, in their personal time. And so in that way, you can sort of jump into their future.
Okay, which is also the principle that they're using in Interstellar when everybody's getting older and they're basically, they're so anxious of getting out of that planet because the
That's right. That's the other way you can do it.
So
you can freeze your personal time by going into a strong gravitational field. You can also maybe freeze yourself and revive yourself, which is a more conservative and cheaper way to do it. Or who knows? Maybe at some point we'll be able to upload our consciousness,
which is also another.
Right. There's no reason from physics why we can't do it. It's just a very difficult engineering problem that we can't accomplish yet.
Yeah, Elon Musk is trying to. Well, not him, of course, but what's
right? That's a human computer interface, direct brain to computer interface.
Yeah, and then one day maybe it goes the other direction.
If we can get our brain scans and modeling and computation all powerful enough, then yeah, that's possible in theory. It's at first it will be very expensive to run a brain. But eventually, things get cheaper. So.
What's interesting about that? It makes me think that actually, in that case, you wouldn't only be able to time travel, but also to
you can copy yourself
in more places.
And that's, for computers, it's no big deal to make a copy of your running program and run it somewhere else at the same time, and maybe meet that program and interact with yourself essentially. So it does not provide any philosophical or conceptual difficulty to a computer that is copying itself and running in multiple places at once. And the whole problem of identity, it's like, oh yeah, there are 2 of me now, there are 200 of me now. There are a million copies of Microsoft Office being run at once, and then that doesn't give them a philosophical puzzle. It's just they're used to it. Whereas for a human being, we're used to there being only one copy of us. So that's gonna be very, very different for us once we can upload our consciousness and make copies.
Good luck with the laws catching up.
Who am I married to? we have to share now?
Yeah, I think they're all gonna commit suicide. Whoever's doing the laws, they're just like, oh, I give up.
Suicide is
or a computer will have to do it.
I've lost friends that way, and it's very horrible. I mean, it's mostly just, it has to do with healthy brain chemistry and social community and surroundings and circumstances. But also, I mean, life is just freaking hard sometimes. Sometimes life is just so horrible, maybe suicide is the right answer. It's hard to say it's not if things are really bad.
No, absolutely. I didn't mean to touch on the subject in terms of course, being offensive or anything, especially if you lost friends in this way. I was just thinking of making irony out of the fact that if we are in a world we can conceive, probably, as you said, there's going to be rates in which our brains won't be able to conceive them. Therefore, we're probably not accept that world.
Yeah, of course.
Maybe that's going to be the easiest
solution.
Sometimes,
I mean, there are a lot of mind-expanding moments that one has growing up. When you start to realize how big the world is, and then how big our solar system is, and how big the galaxy is, and the universe is. And then just how tiny and insignificant our planet and our lives are, both in terms of, physical scale and duration in time. I mean, we're just like an insignificant dust speck existing for an eye blink. And it's just nothing objectively means anything. The only reason we have meaning in our lives is because we created ourselves. Yeah,
I agree with you. I mean, yes, it reminds me also of Pale Blue Dot in terms of amazing quote. Who's never read that? I don't know if it was an article. It's out of a book that Carl Sagan wrote when he commented the picture of the Voyager from
the Pale Blue Dot
out of Saturn. That was picturing Earth, and exactly that kind of concept, which also I think a lot of astronauts, when they get out of space and they realize how small we are
and how fragile
they get that sense. And that also, they're amazing people when they probably even before they went out there, but they come back as really revived in terms of their approach to life, and probably because they realize how fragile
it's really good to be exposed to that sort of perspective.
Okay, Garrett, I am very satisfied with the conversation we just had, and I also am. I really appreciate your time, and really hate taking people's time, stealing people's time like this. So, I think we can call it in now, and I really want to thank you for your time, and
it's very good talking with you, Fabrizio, and best of luck with your podcast.
Thanks so much. I mean, it's as I told you whenever it was your first time, after nothing, just personal discovery and understanding how things work. Also, off records, of course, I'll send you the recording as soon as we're finished. So if there's anything you would like to edit out,
this has been fine. I'm not that particular.
Don't feel.
I'm very open about things.
Okay.
Okay,
okay, cool. Thank you so much again.
Ciao.
You've been really kind. Hope we can ever meet soon. Thanks.